All right, hello math friends. Today we're going to be looking at the derivative of a function. And so last week we had been looking at finding the slope at a single point on a curve. I mentioned that this was going to be known as the derivative later on. So what we have here is what we're going to call the definition of a derivative. Previously, the slope of a curve at a single point, we found that with the difference quotient. So for a given point, we use that limit as h approaches 0 of f of x plus h minus f of x all over h. When that limit exists, we call that the derivative of f at that point a. Now expanding, rather than just for a single point, we are going to say for any point, any value x on the domain of that function. The derivative of a function with respect to a variable x is this new function f. We use this little tick mark, we say f prime. So this derivative is f prime such that f prime is the function where we keep the x value. So we're going to apply this same limit as h approaches 0 for the entire function. We saw this with a preview before when we just said a, and we had some value a that worked out and we kept it in terms of a variable rather than substituting in for a specific value. Now we're saying that f prime of x, the derivative of f of x, is this limit, provided the limit exists. That means left and right sides match up. So the slope is going to work out. Differentiability, a function that has a derivative is called a differentiable. And differentiability has a number of nice properties. It's continuous. It will be guaranteed to be continuous, well, because the limit exists, and also because we have to equal the value at that point. But differentiability is also going to imply smoothness. Local linearity. Now let's go through, try a few examples, talk about a few definitions. Let's use this. So once again, the derivative of a function, we apply this limit as h approaches 0 of f of x plus h minus f of x all over h. Let's apply this for the function x cubed. Pull up math type, try this out. So to find the derivative, we're going to apply this limit. And what I'm going to do is I'm going to substitute in these parts. Rather than f of x plus h, we're going to substitute in x plus h into our function. So it's going to be x plus h cubed minus f of x. That is x cubed all over h. Our task is now to evaluate this limit. So it gives us the limit as h approaches 0. Now what we'll do is we need to simplify this, cancel out, work out, manipulate out that dividing by 0. So if we just use direct substitution, we would have x plus 0 cubed, okay, x cubed minus x cubed, which is 0, divided by 0. We need to do some manipulation to work that out so that we can evaluate our limit. We're going to expand our parentheses, do that multiplication out. It's going to give us x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. What we see, x cubed, okay, minus x cubed, okay, that will cancel. I'm going to copy this down to the next line so we can start our manipulation, make that a little bit easier. That x cubed subtract x cubed will be eliminated. All right, let's do that. That term cancels with the x cubed. All right, factor of h, factor of h, factor of h, factor of h. Everything has a factor of h. So we can distribute and divide out that h. That will leave us with, okay, 3x squared h divided by h will be 3x squared. 3xh squared divided by h is going to be adding 3xh. And then h cubed divided by h, we're going to add h squared. Now, that looks just like a normal polynomial. We can use direct substitution to evaluate our limit. If we substitute in 0 for h, 3x squared remains 3x squared. 3xh multiplied becomes 0, h squared, that becomes 0. We're left with 3x squared. So the derivative f prime of x for the function f of x equals x cubed is 3x squared. 3x squared is the derivative of x cubed at any point. This is a function that gives us the slope at any point of that curve. So the derivative is a function that gives us the slope at a single point for any point x in the domain of our function. Isn't that great? I should put the camera on me. You can see how much I'm smiling right now. But I suppose this is just like wearing the mask. You just can't tell how giddy I am. All right. We also had that alternative definition for finding the derivative or the slope of a function at a point. We also had this other limit when we had the limit as x approaches a of f of x minus f of a all over x minus a. Very similar to the slope formula back from Algebra 1. Well, now we have that limit as x and a approach each other. So we're getting the slope of a single point. So the derivative of f prime of a, we can also use this limit, this difference quotient, to evaluate. So let's go on and differentiate f of x equals the square root of x. We're going to find the derivative of the square root of x. Pull this up. Let's try this out. First, we're going to substitute our function. So f of x is the square root of x. F of a is the square root of a all over x minus a. You might put a sign in there. Now we have this limit. If we attempt to direct substitute x approaches a, that's going to be square root of a subtract square root of a is 0, x minus a, or a minus a is 0. We have 0 divided by 0. We need some manipulation to turn this into something that we can use. We're going to multiply by the conjugate here. Back to our trig identity strategies, sometimes the conjugate will work to work this out. So I'm going to multiply by the conjugate, which is root x plus root a all over the same. Root x plus root a. In the numerator, it is the difference of two squares. So this yields, copy that, square root of x minus square root of a multiplied by the square root of x plus the square root of a is going to yield x minus a. In the denominator, I'm not going to multiply that out. We still have x minus a. Oh, look at that. That's a common factor multiplied by root x plus root a. All right, gave that away. We've got that common factor there. So now I'm going to, next line, x minus a is a common factor that will cancel. This turns into, we've got the limit will be 1 over square root of x plus square root of a. And now, by direct substitution, we substitute in a. We'd have 1 over square root of a plus square root of a would give us 1 over 2 square root of a. Since a is an arbitrary point, we've got the derivative of f evaluated at a. I can substitute back for x. The derivative of x is 1 over 2 root x. So for our initial function, the square root of x, we have come up with the derivative of the square root of x. F prime of x, the derivative of f with respect to x, is 1 over 2 root x. This derivative gives us the slope at every point of the curve, the square root of x. The derivative is a function that gives us the slope at any point along the way. We've got two different, what we call difference quotients, that are used to evaluate limits that can help. Sometimes one is more appropriate than the other. Imagine if we were using the f of x plus h minus f of x all over h term. We would have the square root of x plus h. How could we expand that? We'd have to come up with some manipulation, probably again using the conjugate, but it might not work out as nicely. Different ways have different kind of benefits. Different notation that we'll see over time. we often talk about the graph. And so y can be exchanged, if we're talking geometrically, in terms of, instead of f, which we talk about algebraically, we would read this as y prime. That means the derivative of y. You might see something like dy dx. Say dy dx means d, the derivative of y with respect to the derivative of x, or the difference of y over the difference of x. Think slope is the change in y over the change in x. Sometimes you had the delta symbol, the Greek letter delta, the triangle, meaning the change in, so dy dx. Same, df dx is the derivative of f with respect to x, or d dx of f of x. D dx treats this as an operation. It's take the derivative of the function. So d dx is take the derivative of whatever it's tagged onto with respect to x. We might see something like d dx cosine of x. That means the derivative with respect to x of the function cosine of x. Different notations that we will use throughout our year together. Point out, the derivative is the slope function. Well, we can also graph the derivative. Now, if we compare the graph of the derivative with that of the original function, we see there are some nice connections between them. Finding the graph of the derivative, if we have f, so this first one on the left is y, or f of x. Looks almost cubic. We've got a very steep slope. It's a very steep positive slope here, so we would have a very high positive value. As we move from left to right, our slope is less steep, but still positive. It is still positive slope, but it is less steep, so we have a shallower value. Now notice, graphs from the left to the right. Point A, if we draw the tangent line in, we'd have a slope of 4. The derivative would have a value of 4. At slope B, we're less steep, so it is less positive. Notice that it's marked as B prime. At C, point C, the tangent line would be horizontal. We would have a slope of 0. So there is C prime. We have a slope of 0 for x equals 2. After C, the slope is now negative. We are decreasing as we move from left to right. So the slope, the derivative, would have a negative value. We go from point D, we have a slope of -1. So our derivative would be at -1. Steeper negative, and then we start to curve back up. E is a little bit less negative, back to a slope of -1. Point F, the tangent line would be horizontal, and then it turns to a positive slope again. So positive slope, 0 slope, negative slope, 0 slope, positive. Positive slope, 0 slope, negative slope, positive slope. Follow the cursor on the screen. So the one on the right is y prime, is the derivative. Notice the connections between the slope of a function and that of its derivative. We can use going the other direction as well. Instead of from the function to the slope graph of the derivative, we can go from the graph of the derivative back to the function. Here on the left, we have a graph of a derivative. This is y prime equals f prime of x. Our derivative here, our slope, is at -1, from -infinity up to +1. So we need to have a graph with a slope of -1 from the left all the way to -1. Notice, +1, excuse me. Here on the right, we've got the graph of the function. Our slope of the line on the left has a slope of -1 until we reach x equals 1, at which point the slope of that line switches to being +2. So from at +1, we switch to a slope of +2. So at +1, x equals +1, our graph now has a slope of +2. So we can use that graph to there. Up on the classroom site, there's a little bit of practice. Try it out. Get this idea of the derivative function is a function that gives us the slope of f of x at every single point. The derivative is the slope function. Enjoy.